Hello, everybody. Thank you for your interest and consideration. My name is Ruth, and I'm happy to present this poster, which was the result of one of our group's works. It is titled Green Synthesis of Magnetite Nanoparticles Using Lariata dentata Extract for Arsenic Removal. This study presents the green synthesis of magnetite nanoparticles using Lariata dentata, also known as creosote bush extract. The foregoing as a potential alternative for the removal of arsenic in water, with concentrations that reach up to 1,000 micrograms per liter, which can have repercussions in agricultural soils. For the preparation, we used an aqueous extract of creosote bush leaves and then brought it to a pH of 12. The polyphenols present in the solution are the active compounds that act as reducing and stabilizing agents in the synthesis of the nanoparticles. From the atomic adsorption analysis, values of 71 and 36% removal of arsenic-3 and arsenic-5 were obtained, and respectively turned out to be the highest using a concentration of 0.0125 grams per liter of magnetite nanoparticles at one time of 3 hours. Magnetite nanoparticles have shown favorable activities for absorption and reduction of a large amount of heavy metal ions, such as nickel, copper, cadmium, zinc, chromium, and arsenic, and the catalytic degradation of some contaminants in the environment is commonly due to its adsorption and reduction activities, much better than its traditional macro or micro counterparts. Additionally, magnetite can be easily separated and collected by an external magnetic field. This extraordinary advantage is especially useful for the recovery or reuse of the magnetic nanoparticles. The methodology used is as follows. The sample of bush creosote was first ground with the help of a conventional blender until a particle size that passes through the number 24 mesh was obtained. For the preparation of the extract, we used a plant material to solvent ratio of 1:5 in weight volume with hexane as our solvent in order to carry out the washings and remove the excess fatty acids, mostly resin, present in the plant's biomass. We let it rest for about 5 minutes until the resin present at the top formed a visible layer and then decanted it. This process is repeated 3 times until the solution reaches a uniform crystalline green color. Afterwards, a second wash of the plant is carried out with deionized water in a 1:5 ratio, which was done twice to remove the residues of hexane that remained in the plant solution. Lastly, we take all the precipitate and filter it, and then set it to dry in the oven at 60 degrees Celsius for 8 hours. To obtain the extract, a 1:10 plant material to solvent ratio was used, with deionized water acting as the solvent. This mixture was brought to a temperature of 60 degrees Celsius for 1 hour while continuously stirring, and later let it rest to cool down the solution. Lastly, it was filtered under vacuum to obtain the extract. The synthesis of the nanoparticles was carried out by means of the co-precipitation method, where 2 iron salts are used. In this case, iron 2 chloride tetrahydrate and iron 3 chloride hexahydrate using a 1:2 molar ratio and 100 milliliters of deionized water respectively. Firstly, 99.5 milliliters of deionized water were preheated at a temperature of 80 degrees Celsius, and upon reaching that temperature, the salts are added, constantly stirring for 10 minutes until the solution turns slightly brown. In another flask, 20 milliliters of the salts and 30 milliliters of the creosote extract are added while still stirring, taking on a dark color indicating the formation of magnetite nanoparticles. A solution of sodium hydroxide was added drop by drop in such a way that we adjusted the pH to a value of 12. After this process, the nanoparticles are washed with deionized water 2 times and another 2 times with ethanol. Then they were resuspended in ethanol and left to dry at 60 degrees Celsius for 8 hours. Lastly, the dried particles are macerated and stored in a dry and cool place at room temperature until vials and for further use. For the characterization of nanoparticles, the UV visible spectrum of magnetite nanoparticles was determined by a spectrophotometer VWR UV 6300 PC. The analysis was carried out in scanning mode in a wavelength range of 190 to 1100 nanometers, a spectral resolution of 2.0 nanometers. The formation and stability of magnetite nanoparticles in aqueous colloidal solution was confirmed by the presence of absorption peaks at a wavelength of 270 nanometers, indicating the formation of iron oxide nanoparticles. For the Fourier transform infrared spectroscopy characterization, a Shimadzu model infrared affinity 1s spectrometer was used. The spectrum was obtained by reflectance with the help of a total attenuated reflectance brand accessory from Smith's Quest model with a one-step diamond window. The representative absorption peaks in the Fourier transform infrared spectrum of the nanoparticles are mainly located at wave numbers 3653.18, 1157.3, 1303.8, 741.15, and 582.5. The peak at 3653.18, which is attributed to the presence of a phenolic group in the stabilization process. The strong band at 1741.15 and 1477.8 are identified such as amide 1 and amide 2, which arise due to stretching vibrations like the union of a carbon and oxygen with a double bond group with the nanoparticles. The peak in 1423.11 is attributed to the asymmetry and co-stretching vibration symmetry of a negatively charged carboxyl group. The 1303.8 band can be assigned to the symmetric carbon-oxygen with a single bond vibration associated with a carbon-oxygen-carbon-nitrogen group. The presence of magnetite nanoparticles can be seen by the absorption band in 582.5, which corresponds to the iron and oxygen stretching band of bulk magnetite. These results revealed that the carbon-oxygen with the double bond groups were bound on the surface of the magnetite particle. In general, this observation confirms the presence of protein in the leaf extract, which acts as a reducing agent and stabilizer of nanoparticles. X-ray diffraction of the nanoparticles was characterized in a Philips Expert MPT diffractometer equipped with a graphite curve monochromator with a copper grid that has a lambda of 0.154056 nanometers. The magnetite with average crystalline size equal to 26.32, 43.86, and 104 nanometers respectively, according to the Schroeder equation. Furthermore, it is found that all the reflection peaks in 220, 311, 400, 422, and 511, as well as the 440 planes, are related to the inverse spinel cubic structure of the magnetite nanoparticles. The quantification of the concentration of arsenic 5 and 3 in representative solutions of agricultural soils was carried out with contact tests to measure the absorption of arsenic using atomic absorption spectrophotometry equipment with a graphite furnace in a GBC scientific model collection rate of 9 microliters per second and a sample volume of 30 microliters. As seen in this table, an optimal time of 3 hours was obtained for arsenic 3, obtaining a removal of approximately 70%, which by increasing the contact time, the removal decreases. It could also be observed that the optimal concentration of magnetite nanoparticles is at 0.0125 grams per liter, with the best conditions to obtain the greatest removal of arsenic-3. In the table, we can see that for arsenic-5, the optimal time was also 3 hours and the same concentration of 0.0125 grams per liter of magnetite nanoparticles, obtaining a removal of 36%, with arsenic-5 being the most difficult to attract by nanoparticles. As a conclusion, we now know that the removal percentage achieved in arsenic solution was 70% for arsenic-3. This work allowed us to determine the viability of the application of nanoparticles of magnetite synthesized based on a laurea dentata in the absorption of arsenic in agricultural water, where we realized that it has a high absorption potential for this metal. Thank you so much for your attention.